Okay, enthalpy of hydration, another enthalpy change associated with ionic compounds that you are expected to know about, be able to define and represent and discuss and compare different ions for how big their enthalpies of hydration would be. So, the enthalpy of hydration is the enthalpy change when 1 mole of gaseous ions is completely mixed with water. So, represented in an equation, it is the enthalpy change, the delta H, when ions, like sodium ions here in the gas phase, become sodium ions in the aqueous phase. So when they're fully dissolved in water, when water and ions interact, they have ion dipole interactions. So it's a type of attraction that's being formed. So again, if you want to think about pausing this video, can you answer the question, is this endo or exothermic without looking at the tables? Although I see that they're probably right in front of you. But if you had to guess, is it exo or endothermic, you should be able to figure out that it's exothermic, because the process of going from being gaseous ions, where all the ions are separate from each other, and then they are forming attractions and coming together with water molecules. So anytime we bring particles together, that's going to end up releasing energy as a general rule. And sure enough, if you look at table 20 of the data booklet, all of these values are negative. So we should know what enthalpy of hydration is, its definition, how to represent it with an equation with correct state symbols, and we should know, generally speaking, that it is exothermic. The next thing you have to be able to do is compare the relative size of enthalpies of hydration. And so if you look at this table, first thing you can see is right here, all of these are alkali metals, and I can see that going this direction, they are decreasing. I would also kind of notice that going here, I'm going down the periodic table, and so the first thing that makes me think of is that I'm increasing my ionic radius. And so what we're going to notice is that we're going to see the same trends here as we do with the lattice enthalpy. So what I see with that first one is that if I flip around how I described that, it's nice to talk about things increasing. As I go up the periodic table, up group 1, so I get smaller and smaller ionic radii, I'm going to see that the values for enthalpy of hydration increase. So as I shrink the ionic radii, I increase the enthalpy of hydration. The next thing I want to compare is charge on the ions. If you look at the 1+ ions, and then you get to the 2+ ions, and then you get to the 3+ ions, you should see that when you go from 1+ to 2+, you get a big jump in how big the magnitude is. And when you get to 3+, you get significantly higher still, right? So these are 1+ ions, 2+ ions, and 3+ ions till here. And if you do the same thing over here, there's probably some that we could look at. Yeah, we can see we've got our minus ions, 1- ions here. If we go down, eventually we get some 2- ions. They're much higher, and then eventually we get a 3- ion at the bottom with phosphate, and we can see that that same trend holds true for the anions. So just like before, as we increase ionic charge, we also increase enthalpy of hydration. So same idea as lattice enthalpy. Smaller ions with greater ionic charge have greater charge density. And in the same way that greater charge density will lead to greater electrostatic attraction between ions, as we increase the charge density, it will also lead to greater attraction between the ions and water. So increasing the charge density increases the strength of those ion dipole attractions, and therefore it increases our enthalpy of hydration. And that's really all you need to know about enthalpies of hydration on their own. They will combine with the lattice enthalpy into an energy cycle, but this video is just about the enthalpy of hydration.